Chapter 13, Question 7, asks you to identify the chiral carbon in each of the following naturally occurring compounds. And there's a key word here that's really important, and it is chiral. So let's talk about that for a second. The word chiral just means handed, and it comes from the Greek word for hand. So chiral just means handed. Now if you look at one of your hands, it has 4 sides. You have the back of your hand, the palm of your hand, the thumb side of your hand, and the pinky of your hand. 4 different sides. Four different sides. And there is a geometrical phenomenon. If anything ever has 4 sides, it can come in 2 different forms. It can come in a left-handed form, or it can come in a right-handed form. Both of your hands have the same type of sides. They both have backs, they both have palms, they both have a thumb side, and they both have a pinky side. But they're different things. If you ever try to put your right hand into a glove made for a left hand, you'll see that it doesn't fit and that your hands are really different things. Anything can be chiral, anything that has 4 different sides. So for example, your feet have 4 different sides. The top of your feet, the bottom of your feet, the inside of your feet, and the outside of your feet. And again, if you ever try to put your right foot into your left shoe, you'll see the importance of chirality. Right-handed things don't fit into left-handed pockets, and left-handed things don't fit into right-handed pockets. Now, there's one element that often has 4 different things attached to it. In other words, has 4 different sides and is chiral. And that is carbon, because carbon can have 1, 2, 3, 4 total bonds. So if the things bonded to it are all different, and only if they're all different, then that carbon would be described as chiral. That would be a chiral carbon. And there would be 2 versions of it, a right-handed version and a left-handed version. And just like your right hand won't fit into a left-handed pocket, a chiral carbon that's right-handed won't fit into a left-handed enzyme pocket. And that can make a huge difference. There are some drugs, for example, thalidomide, that are used to treat things. Thalidomide is used to treat nausea in pregnant women. It has a chiral carbon in it, and one of the hands will fit into the enzyme pocket that helps to treat nausea. But the same molecule, just with a different handed carbon there, instead of the right hand, the left hand, for example, causes birth defects. So whether these molecules, these messaging molecules, fit into enzyme pockets or not, or fit into pockets on the surfaces of cells or not and communicate messages, depends on whether they're the right hand or the left hand. And so the handedness of molecules, the chirality of molecules, is really, really important. Almost every biological molecule is chiral. Biological molecules are incredible. There's so much chirality in them. Sugars have a lot of chiral centers. Lipids have chiral centers, and almost all proteins have chiral centers too. So let's see if we can try to identify some chiral centers now that we know why they're so important. What we're going to do is go 1 carbon at a time and see if it's bonded to 4 different things. So let's start at the left. This carbon here. Let's see if that's a chiral carbon. Well, it's bonded to a hydrogen, that's one thing. Another hydrogen, well, those are 2 of the same things. Another hydrogen, that's 3 of the same things. So clearly this is not going to be bonded to 4 different things. The other thing it's bonded to, this huge group here, is definitely different from the hydrogens, but that's only 2 different things. You have the hydrogens, and then you have that big weird group. So that carbon is not chiral. Okay, let's see if this carbon is chiral. So this is going to be bonded to a CH3. Notice that I'm thinking globally here. Another CH3, so already not looking too good for being chiral. And then this third one is different. You have this big, huge group. But that's only 2 different things. You have the CH3s in that sort of gray, And then you have that gigantic weird purple thing. So it's 2 different groups. In order to be chiral, you have to have 4 different groups. That carbon is not chiral. This carbon, let's see if that's chiral. Okay. On the left, we have a very big weird group here. On the right, we have another very big weird group that is completely different. So notice I'm thinking very globally here. Anything attached to this carbon all together. And then last but not least, we have a third different group. We have this hydrogen here. But that is only 3 different things, not 4. And so this is not chiral. Remember, to be chiral, you have to have 4 different groups bonded to it. 4 different groups. Okay, let's see if this is chiral. Well, we have hydrogen. That's one thing. We have another hydrogen. That's a second of the same thing. We have this gigantic group here, which is definitely different. And then we have this gigantic group on the right, which is different. But you can see that that's only 3 different things. There are only 3 different colors here. And so that is not chiral. You need to have 4 different things, 4 different groups bonded to a carbon in order for the carbon to be chiral. By similar logic, this isn't chiral. So a faster way maybe to think about this is carbon has 4 bonds. If it is bonded to if it's bonded to the same thing twice, then it can't be chiral because it can only have a maximum then of 3 different things. So you notice that this carbon has the 2 hydrogens. So no matter what, it's not going to be bonded to 4 different things. It's not a chiral carbon. All right, let's think about this one. We have a CH3 on the top. That's one thing. We have this weird group on the right. Definitely a different thing. We have the hydrogen at the bottom, also a different thing. And then we have this gigantic group on the left. That's a 4th different thing. Notice that there are 4 different colors here. This is very definitely a chiral carbon. So that carbon is chiral. I'm going to leave that dot here. This is totally chiral, actually. This is a chiral carbon. If we play the same game with these others, we'll see that here we have 2 hydrogens, so it can't be bonded to 4 different things because it has 2 of the same, so that's not chiral. And then with this last carbon here, it's bonded to 2 of the same thing, so it can't be bonded to 4 different things, so it's not chiral. So we only have 1 chiral atom in this citronellol. Next, alanine. This is an amino acid. Let's go through this. On this first carbon, we see that we have 3 of the same thing. So there's no way that that carbon is going to be chiral. It has to have 4 different things in order to be chiral. This carbon has a CH3, so that's one thing. It has a weird sort of carboxylic acid group to the right. That's a second different thing. It has a hydrogen. That's a 3rd different thing. And then it has this nitrogen group. That's a 4th different thing. That has 4 different things, and so that carbon is indeed chiral. So we can say this carbon here is chiral. If we look at our last carbon here, you can see that that has the OH, that's one thing. It has an O, that's a second thing. It has this gigantic big group, that's a 3rd thing, but that's it. That's only 3 different things. In order to be chiral, you have to have 4 different things, so that carbon is not chiral. So the takeaway message is, go 1 carbon at a time, look at all the groups attached to it globally, the whole group. It has to be bonded to 4 different groups in order to be chiral.